All right. I think it's night too. Let's get started. So good morning, everyone. Hope you all had a great weekend so far, and welcome to the Friday seminar of Bureau of Economic Geology at UT Austin. And I'm Chen Yang, the host for today's seminar. And today we're so glad to have Dr. Toti Larson as our speaker. So just to introduce Toti, Dr. Toti Larson is a research associate and principal investigator of the Mudrock System Research Laboratory Consortium at the UT Austin Bureau of Economic Geology. And Toti received his PhD from the University of New Mexico with a focus on stable isotope geochemistry. Prior to the Bureau, Toti was a postdoc at the University of Western Ontario, a research scientist at the Los Alamos National Laboratories and the Department of Geological Sciences in the Jackson School of Geosciences. And Toti has conducted a wide range of studies that include metamorphic petrology, carbon sequestration, chemical weapon, forensics, distribution of uranium deposits in sedimentary systems, and dissolved gas geochemistry in subsurface systems. And Toti's current research focuses on the geostratigraphy of Mudrock system, and he applies machine learning tools to integrate core-based measurements to characterize the positional settings of Mudrock system. And in his free time, and Toti plays flatpick guitar in a bluegrass band and trades cryptocurrency with his son. That seems a lot of fun. So yeah, Toti will give a presentation in the next 40-ish minutes. If you have any questions or comments during his presentation, please put them in the chat box, and we will get back to the questions in the Q&A sections right after the presentation. All right, Toti, the floor is yours.
Yeah, well, thank you very much, John and Kelly, for volunteering and hosting the technical series. It's not an easy job, so appreciate the efforts. Let me share my screen. How's that?
Looks good.
Okay, great. All right, well, good morning, everybody. My name is Toti Larson, and in this presentation, I'll provide results from a machine learning core characterization workflow that's been developed in the MSRL consortium at the BEG. In addition to my co-authors listed here, this work was accomplished in collaboration with James Green from New Tech Energy, who provided MICP results, and Jonathan Knapp from Bruker Nanoanalytics, who's been collaborative in the science of defining chemofacies. This talk is focused specifically on Wolfcamp XY and Third Bone Spring sand in the Delaware Basin, but the workflow is being applied to Wolfcamp A and B in Midland and Delaware Basin, Second Bone Spring lime in Delaware Basin, Eagle Ford Shale, Austin Chalk in Central Texas, and the Vaca Muerta in Argentina. So the workflow, the methods, and the data sets that we have access to they're expansive in nature and widely applicable to Mudrock systems around the world. I'm going to cover a lot today, but there's three key points of this talk that I want to highlight. And they're sort of the research goals of the project. First is that we're developing formation-specific training data sets that integrate a wide range of core data. And this includes high-resolution X-ray fluorescence core scanning, mineralogy, organic matter richness, porosity and permeability core data, and MICP data. We're using machine learning classification, specifically the XGBoost Decision Tree classification, to build chemofacies that capture important reservoir quality and geological attributes. Secondly, I'll outline a workflow and show results of how we integrate wireline petrophysics data into the chemofacies model to inform wells that don't have core. And I'd say this is one of the bigger advances that's coming out of this work, and it's allowing us to incorporate thin bed heterogeneities that are typical of Mudrock systems into petrophysical wireline models. And this gives us an approach to upscale core data beyond the core. And then finally, we'll look at how we can predict chemofacies distributions across the basin and how we can use this information to inform basin scale geological models and understand how the spatial distribution of chemofacies will ultimately affect reservoir quality. Let me see if I can get the screen pointer. Okay. Okay, here's an overview of the study area, and it's shown here in red. We'll be focusing in on the Delaware Basin. It's all contained within the Permian Basin, kind of shown in this sort of grayish area here in West Texas. The Third Bone Spring sand and the Wolfcamp XY are Leonardian in age, and they were deposited as the global climate was transitioning from icehouse conditions to greenhouse conditions. There were still very large-scale fluctuations in sea level, and all this had an effect on sediment routing and carbonate productivity on the surrounding carbonate platforms, including the Central Basin Platform, the Diablo, and the Northwestern Shelf. But here in this talk, we're going to talk about the deep water deposits that infilled the Delaware Basin during the Leonardian. And what's important to understand is that the depositional history here is complex. You've got multiple sediment sources that range from carbonate to siliciclastic, water chemistry that can vary depending on degree of basin restriction. Organic matter productivity is going to change. There's different mechanisms of sediment gravity flows, and collectively, all these changes and variables result in heterogeneous mudrock deposits at the thin bed scale. And what we want to be able to do, sorry, I keep moving my slide up. I'll go back. There. So this variability in depositional system, it results in this very heterogeneous thin bed heterogeneity that exists. And what we want to be able to do is capture this thin bed heterogeneity and use it to better inform reservoir systems. And one note for those who are unaware, this field area is completely subsurface. And so all the information, all the data that we've got access to inform this basin, or that I'll be talking about, are either core or wireline logs. This slide here is just to show how I define Third Bone Spring sand and Wolfcamp XY. These are resistivity and gamma ray logs. So resistivity in green, gamma sort of in this shade of purple. The strategy I use is based largely on the work of Shane Ance and Scott Hamlin, and is published here in Anatomy of the Paleozoic Basin. And what you can see here is Third Bone Spring sand has a sort of low resistivity swoop. It's relatively easy to track across the basin, and it has a drop in gamma ray. And here's just a type log for kind of northern Delaware Basin, Eddy County, and here's another one in Reeves County. And these are both published by Shay and Scott. The East Vermejo core, I highlighted, it's a different scale than these two right here, but I highlight this to show how I break out Wolfcamp XY. And it's done solely from gamma ray logs and resistivity from the, showing it for the East Vermejo. Both Wolfcamp Y and Wolfcamp X are contained within Wolfcamp A, but both of them have this sort of resistivity or a gamma drop followed by a resistivity high. You can see one for Wolfcamp Y right there. I keep hitting that button. And you can see another one for Wolfcamp X. And what that is a sequence of quartz-rich siltstones on the bottom that's overlain by mudstones over on the top, those sort of gamma highs. And I think of this in a sort of sequence stratigraphic framework with low stand sands entering the basin followed by a transgressive sequence and the deposition of the mudstones. And then finally, you can see the big gamma drop that happens at the onset of Third Bone Spring. And really, when Third Bone Spring came in, I mean, it's a fundamental shift in deposition for the Delaware Basin from the more calcareous-rich mudstones that are typical of Wolfcamp B, Wolfcamp A, into just these detrital-rich quartz siltstones. Taking this on a sort of north-south transect from Loving County, Ward County, Reeves County, and down into Pecos County, datums off the base of the Third Bone Spring sand, which you can see is a general decrease in thickness of Third Bone Spring, going from 300 feet or so to the north down to about 200 feet down to the south in Pecos County. But what really changes over this transect is the overall thickness of Wolfcamp Y and X. Wolfcamp Y shown here in yellow, Wolfcamp X shown here in white. And you can see it goes from nearly 200 feet thick in Loving County to basically non-existent as you make your way down into Pecos County. Also shown in here are the locations of the cores that I'll be talking about, and they're highlighted here in the red. And this kind of paints part of the picture that we're trying to solve here. And what you can take away from this is the problem we're trying to solve. We will always be limited in core data, but the core are the most data rich. And so somehow we got to come up with a means to better capture information and data from the core and use that to inform wireline logs across the basin. we're always going to have more wireline logs than we'll have core. And the approach that I'm going to be showing here is one approach that I think is could be successful using chemofacies. Another thing to take from this is that even within a single formation, there's just going to be a dramatic difference in the sort of spatial distribution of these facies across the basin. So looking more at the basin scale, here are some Isopack maps for Wolfcamp XY and Third Bone Spring sand. The scales here are different. The color bars here go from 0 to 250. The one here goes from 0 to 500. So what you can kind of see from this in Wolfcamp XY time, you basically have the deposition of this submarine fan complex that's infilling the basin from the north. You know, maybe there's a sediment pathway from the northeast, but it's really filling up the basin from the north, and then the deposits thin dramatically as you get to the south, basically to non-existent. Non-existent being, you know, it's about 25 feet thick, maybe 50 feet thick here, and then it's pretty tough to pick it out here, and it's, you know, less than 10 feet if present. Third Bone Spring is a little different though. It still is thickest to the north, but still, as you get down to the Pecos kind of Reeves County line, you're still at 200 feet thickness of Third Bone Spring sand. And so it's more of kind of filling up the basin just like a sheet. And so again, from this, what I'm taking is that even within a single formation, you know, with this different depositional style from the submarine fan complex up to the north to this more distal basin deposits here, even within a single formation, there's going to be a lot of heterogeneity and a lot of change in the facies distribution across the transect. And so it's important to capture that change in facies. And this slide here kind of captures the workflow that we're doing here. The slide in the middle, I think, is the one that's most important and kind of shows the advantage of working in a chemofacies framework. What's shown here is a 600-foot core, and you can see that we've got these white stickers spaced every 2 inches. Every one of those stickers, we can use X-ray fluorescence and measure the composition of 30 elements at each one of these stickers. And so what we have here is a statistically unbiased characterization of the core. And this is in contrast to what is typical with core plugs. And here's just a picture of what core plugs look like. You know, core plugs are taken certainly at much lower resolution. And I'd say it's nearly impossible to completely impossible to, you know, statistically capture the variability in a core in a representative fashion by taking core plugs alone. It's just, you're never going to be able to sample enough, and you're never going to capture all that thin bed heterogeneity that we know exists. But by integrating core plug data with high resolution X-ray fluorescence and a good chemofacies model, we can remove the spatial bias, and then we can start to representatively describe rock attributes across the entire core interval. And so chemofacies, as I'm applying them here, really serve the purpose. It's almost like a middleman in the operation. It is basically used to capture the variance or the variability across the entire core, and it's used to sort of bin and cluster the rock attributes. So we can take these rock attributes and describe it across the entire core, and then we can get into these applications. And there's 3 of them. I'm not going to work on drill cuttings or describe drill cuttings, but, you know, applications include training wireline logs, interpret depositional systems, and then a new project that we're getting into is evaluating drill cuttings. So I've probably said chemofacies 100 times, and I haven't even said what they are. Well, a chemofacies it's a mappable rock unit, and that is defined in terms of unique geochemical composition. It's nothing new. The International Commission on Stratigraphy has a very specific name for chemofacies, but it's really important to think that what is driving chemofacies is the chemistry. So they're these sort of mappable units that are distinct chemically. Okay, in this slide here, we're talking about the machine learning workflow. Machine learning is a big part of this research, and it's a tool that lets us integrate the wide range of data sets that we've collected, and it also allows us to develop these chemofacies. There's no way we could accomplish this work without machine learning. It just wouldn't be possible. And for reference, on a 300-foot core, the high resolution XRF generates about 54,000 data points in 30 dimensions. When you add in the mineralogy, the organic matter characterization, porosity and permeability, you gain at least 20 more variables. Tie in the wireline logs, your dimensional space increases even more. And it's just not possible to put all these variables and these data together without advanced multivariate statistics and machine learning tools. And so that's going to be the focus. Now, machine learning doesn't have to be scary. It certainly has a black box element to it. I think that's what turns people off to it. But quite frankly, the style of machine learning and what goes on in machine learning, it's been going on forever. And so just take this easy scenario here. This scenario we've all been in. This is a scenario that we've all been in at one point. You drop a piece of food on the floor. Okay, what's the question? Well, do you eat it or do you not eat it? First question, of course, you can ask yourself is, did anyone see you? And if not, well, was the floor sticky? There's a whole set of questions you can ask yourself whether or not you're going to eat that piece of food. And really, the classification is two in this case. You're either going to decide to eat it or you're going to decide to not eat it. But you're going to have this sort of decision tree that's going on in your mind that's going to be used to define whether or not you eat this piece of food that hits the floor. We're doing the exact same thing. It's more advanced, obviously, when we're tying this in with the chemistry, but it's the exact same thing. It's just that the decisions that are being made are going to be based on elemental compositions. I've done a few different versions. When I started this game, neural network is how I ran, and I still do use some neural networks, but I've moved to decision tree and specifically XGBoost Decision Tree, and for a variety of reasons. One of the advantages is that it's not as black box as neural network. You can actually go back and you can see what the decision tree is basing its decisions on. And so that's really important to kind of gain when people ask, like, how are you defining your chemofacies? Decision tree lets you see that. Another really important thing here is that in decision tree, you can add categorical data. All the work and all the results I'm going to show today are going to be based on chemistry. They're going to be tied to the rock fabric, but the rock fabric itself is not being incorporated into the training data set. It's just being used to validate my results. But with decision tree, I can add in rock fabric. And so now we can really start to go beyond just using chemistry to define the chemofacies. We can use the chemistry, and then we can take other core descriptive attributes like rock fabric. And I think this is where it's going to get really important as we start doing this. We're going to get better and better answers and better classifications that are going to tie to these reservoir characterizations that we're trying to do. And then finally, scaling data. You don't have to scale data in decision tree. You do in neural network. And this was one of the weaknesses I found. I could use neural networks when I was running chemofacies just off XRF data. But when I started running the neural networks on wireline logs, sometimes it worked really well if I had really good control on the wireline logs, but I had a few just catastrophic failures. And I think the issue there was the scaling. And I was able to run it again using decision tree, and I was much happier with the results. So for the rest of this talk, we'll be talking about decision tree. Okay, so chemistry. We're going to dive right into it. Here are the chemofacies results from the decision tree model that I've run off of a supervised training data set that I built from the East Bermejo core. This core covers most of the third bone spring sand, not all of it, and it covers Wolfcamp X, doesn't cover Wolfcamp Y. I can add additional data to the training data set from cores that cover Wolfcamp Y, and that's kind of one of the advantages of working in a training data set kind of framework, is that you can continually add more and more to it. So these things are living and they grow as you learn. This is one of the key advantages of working with training data sets. But let's sort of start here and kind of look at how the chemofacies are defined. I've got 8 chemofacies kind of color binned here. Don't worry so much about the names of it, but I'm doing my best to try to use the names to describe what we're looking at. But starting from the top left, this is a really common biplot that geologists use to look at mixing models in mixed calcareous siliciclastic systems. And what you can see here is you start at the top left, you have this really silicon-rich chemofacies shown in this aqua. These are going to be the quartz-rich, detrital quartz-enriched siltstones. And as you move down to the right, you're picking up a lot more aluminum. So these are going to be the aluminous, silicious mudstones over here. And as you work your way down to the bottom, these are going to be the chemofacies with the least amount of aluminum silicon. Turns out they have the most amount of carbonate. And so really what this trend here is a kind of a carbonate mixing trend between carbonate-rich and siliciclastic. And then you got this other mixing trend of different types of siliciclastic minerals. And tucked inside of it, you got the orange, the purple, and the green chemofacies. We can go down to this biplot down here, which shows magnesium versus calcium. And now you can start distinguishing out and figuring out what exactly is this red chemofacies. And you can see the red is enriched in magnesium. These are likely to be dolomitic, whereas the orange has a lot of calcium, but doesn't have a lot of magnesium. And so these are likely just going to be calcite rich. This one here, this purple one, I don't know what it is. It's got elevated magnesium. It's kind of midpoint in calcium, so it might be dolomitic, it might be chloritic, but I can go back and make thin sections of this, or we can do SEM or XRD, and we can better define the mineralogy there. Kind of working around the wheel, looking at molybdenum and nickel. You can see we've got these in pink, these data points that are elevated in molybdenum and nickel. That's going to be important in terms of thinking of bottom water chemistry and possible organic matter richness. And so I cluster those out. Finishing it off, there is this gray chemofacies that's tucked inside here, which is really not distinguished on any of these plots here. This is a really important facies across the Leonardian in both Midland and Delaware Basin. And these are these laminated detrital quartz siltstones. And so as I was building the trained data set, it was important for me that I could distinguish this one out. And so I built this in a supervised fashion. And I specifically defined and picked laminated quartz siltstones and labeled them as such. And even though you can't see how the decision tree is picking up the that siltstone, the fact is it is, and I'll show you in the core photographs how it is. And really what that's telling you is that there's a dimension here that you're not picking up. And consider that we're working in 26-dimensional space. And so there's more going on behind the scenes than you can visualize in these 2-dimensional plots. And that's just something you have to get comfortable with when you work in multivariate space. So right now we've only talked about chemistry, aluminum, calcium, magnesium, elemental concentrations, but we're following the hypothesis that mineralogy, organic matter content, and rock fabric are correlated to rock chemistry. This is the big hypothesis that I'm chasing. I think it works, and I'll show you some pictures of why I think so. Before I do that, let's just finish off the trained data set. You want to be able to validate your models. And that's what's important, that I found at least important, with working with decision tree versus neural network. In decision tree, I can see the feature importance. And so these are ranked in terms of how many times this element, so calcium, for example, how many trees is calcium involved in one of these decisions? And you can see it's involved in 49 of them. So it's a lot of the decisions are based on calcium, followed by nickel, magnesium, molybdenum, zirconium. And so you can see that the calculations are being weighted heavily by these elements here and less so on these elements here. One note is that there's only 26 elements on here. XRF gives you 30. There's some elements that just aren't worth looking at. And they aren't worth looking at either because they're potentially going to be contaminants. So barium, for example, would be one. Or there's some elements that if you just don't understand their behavior in these rocks, take it out of your system. There's no reason to base decisions based on things you don't know. And so what I'm doing here is I'm adding a lot of the elements. I mean, I'm up to 26, but I'm really focusing on the elements that I understand as a geochemist. Another way you can validate the model is through a confusion matrix. And with a confusion matrix, you're taking a test data set and you're running your model against it, and you're finding out how many times is it predicting what the actual chemofacies is. And so this diagonal is what's important. This is how many times it's getting the answer correct. And so the answer is generally good. But what's nice about this is you can start looking to see where it's screwing up and where it's making these errors. So for example, chemofacies 0, this is that argillaceous silicious siltstone. You can see most of the time it's predicting correctly, but some of the time it's predicting that it's chemofacies 5, which is that laminated quartz siltstone. And so I can run over here and find out it's that, and then I can find out actually that laminated quartz siltstone is overlapping with this. And so I can see where the model is getting confused, and I can start to edit my trained data set if necessary to improve that. And so there's a lot of ways to validate the model. Okay, we're done with chemistry and machine learning for a while. I know there's a lot of geologists here, so let's look at the rocks. One of the things that I built with Python in this package that I built is called CorePy. And I built this in part, this part here in collaboration with Priyanka Parwal, who also works at the BEG. She helped me make it so that we could take core box photographs, we could crop them, and then we could add directly the chemofacies results on top of the core box photographs. And so what you're seeing here is everywhere, you can kind of look behind it, you can see a little white sticker. Everywhere you see a white sticker, that's where I took an XRF data point. And then the color-coded square on top of that is my chemofacies. And so this is part of my validation that I've built. It allows me to go back to the core and look and see what the chemofacies are. And that's what's allowing me to understand how the fabric is relating to the chemofacies. And so this is an attempt to start marrying or merging, chemofacies and lithofacies. There's still different ways to categorize, but we kind of want to bring these two together. So working from the bottom of the core, we are in the this section right here, the core. This is covering the sands part of Wolfcamp X. And we'll kind of start from the bottom. What you can see is that this aqua color, these are these quartz-rich detrital siltstones. And you can see there's a really sharp contact, and these sands come in. It's a hybrid event bed of some sort. Comes in, fills this area up with these kind of massive, sometimes they're laminated, sometimes they're unlaminated silt-sized sands, and these grade into the blue chemofacies, which are the mixed argillaceous silicious mudstones. This is a complex chemofacies. It's got a lot of fabric. You can observe a lot of shear. There's dewatering structures. There's these sort of water elution pipes. A lot of evidence for shear. It's a very complicated chemofacies, and it's commonly associated or on top of these detrital-rich sands. Here is this pink chemofacies that I mentioned is enriched in nickel and molybdenum. And so again, it's a different type of mudstone, still mudstone, just like the blue is, but it's a different type of mudstone. So we're starting to use the chemofacies to identify different mudstones. I map out a flooding surface over at this point, and this is where we get into the mudstones that are on top of Wolfcamp X. Remember in that earlier slide, I said, each of these X and Y sequences have this sort of siltstone base, and then there's overlap by mudstone. The mudstones on top look a lot like, well, the mudstones on top that are contained within Wolfcamp X look a lot like the carbonate turbidites that you find across Wolfcamp A. So I think there's a connection there that is going on in terms of depositional style. And what you see here are these sort of meter scale turbidites, kind of calcareous wacky stones and pack stones on the bottom that are overlain by more calcareous mudstones. And you can see that based on the orange and the green. The green was that sort of mixed silicious calcareous mudstones. And then boom, another turbidite comes in. A lot more of the nickel and molybdenum rich mudstones kind of found within here. And this sequence just continues. Moving further up the core, we're still over here in Wolfcamp X mudstones. It's that typical motif similar to Wolfcamp A, meter scale carbonate turbidites, a lot more calcareous input. We get to the top of Wolfcamp X, which in my naming is the same as the top of Wolfcamp A. And that's where we hit this, you can interpret it as sequence boundary, but this big dolomitic interval that's on top. And then that dolomitic is indicated by the red chemofacies and also the purple chemofacies, which might be chloritic, might be dolomitic. More work needs to be done on that. And then we hit the third Bone Spring sand. And that's where, you get these big detrital sands coming in. They're all overlain by these sort of mixed, I just keep moving that slide. That mixed argillaceous silicious mudstone up on top. And that motif continues throughout the third Bone Spring sand until you get to the top and it starts to get a little more calcareous. I mentioned this laminated detrital quartz siltstone, and that's shown right here in gray. Now, if you've worked throughout the Sprayberry or the Dean or third Bone Spring sand, you see this in all the cores. It's a big important facies across the Leonardian. And in core, it looks like this sort of laminated, horizontally laminated siltstone. When you look in thin section, it is laminated, but a lot of it is contained in these sort of kind of anastomosing sort of bundles or class, quartz-rich class that degree of lamination. I mean, you can see it right there, but a lot of that lamination goes away when you look much more closely. I don't know the depositional environment for this, but what I'm happy to show is that the chemofacies will actually pick this out. And you can see that it's picking out pretty well. These are all predicted chemofacies based on chemistry alone. And so this is showing you, that hypothesis that I mentioned of can we connect the chemistry to the fabric? I think the answer is yes, we can. So I'm happy with that. Another one that I mentioned are these dolomitic calcareous mudstones, and I just sort of highlight where they are. You see them across the core. If you hit them with your finger or your ring, they sound different. They're dolomitic. They're really brittle. They're really dense. And Lucy Coe has done some petrography on this and has identified dolomite under thin section. And so we do know, in fact, that they are dolomitic. More work needs to be done to understand kind of what the origin of this is. You know, is it just dolomitic cements, or are these detrital grains that are maybe being shed off the platform during low stand systems? I don't know that, but I know that I can pick them out through my chemofacies model. And I do want to do kind of more detailed work to understand these dolomites and their importance. But I'll go into some of the rock attributes and show their importance in terms of reservoir quality. And then finally, I mentioned those carbonate turbidites within Wolfcamp X, sort of those mudstones on the top of Wolfcamp X. And I won't dwell too much on this, but really what I want to take home is that not all mudstones are the same. They all have different attributes. When you look at them under core, they may look the same, but when you start looking at the chemistry, and then when you start looking at the organic matter content and the porosity and permeability, they are different. And so it is really important to be able to distinguish out the different mudstones, you know, if you're trying to, you know, better inform reservoir quality and then capture this thin bed heterogeneity. And you can see, God, I keep doing that there. And you can see that it is relatively thin bed. I mean, you know, 6-inch sessions of this molybdenum rich and 4-inch sessions. So they're present, but the pink and the green chemofacies is predominantly contained within these this sort of Wolfcamp X mudstones. Okay, that is the my connection between the chemofacies and the lithofacies in the fabric, and you can see how I validate the chemofacies that I define. Now we're going to start getting into reservoir quality, and to do that, we've got to integrate core data into the chemofacies motif, and that's one of the advantages of kind of working here in the style that we're working. Every time there's a core plug available or there's been a sample that's been taken, we go back and we XRF where that sample was collected. And so we can directly add that rock attribute data into our chemofacies model. And so now we can bring whatever attribute is measured, you know, and any kind of core plug, could be anything, we can bring into the chemofacies model. Here, I'm just going to highlight a few: total organic carbon, total clay, and porosity, and kind of use this to sort of describe, you know, what the chemofacies are. And so you can see in terms of total organic carbon, that pink chemofacies, that was that nickel molybdenum rich mudstone. That's the most TOC rich, you know, has a median value of about 3, quite a bit of variability across it. The blue chemofacies, the orange and the green, you know, still 1.5 median value of TOC, so much lower, but, you know, still a significant amount of TOC in there. Looking in terms of total clay, that blue chemofacies, that was that really complicated one with a lot of fabric, silicious argillaceous. Certainly a lot of clay in it, but so does this chemofacies here. But then when you get down to the detrital enriched siltstones, you know, those have the least amount of clay, and then those dolomitic mudstones also have a little bit of clay. So what you're seeing here is that we're statistically describing the chemofacies with attributes, and so we can use this statistical distribution to upscale and to model. And that's where we're going with this. In terms of porosity, in terms of defining reservoirs, you know, really good porosity in the East Vermejo core for the siltstones, those laminated siltstones, and those mudstones. And you're going to see how different the permeability is for these in the follow-on slide. But the dolomitic mudstones, these have the lowest porosity in the system, about 4. And I'll just note, this is all from the East Vermejo data. So this is Third Bone Spring up higher on that submarine fan complex that I described. And so we can start thinking of the chemofacies in terms of reservoir quality. I don't have anything for the calcareous mudstones. I don't have enough data for the calcareous mudstones, so I need more there. But we have kind of the dolomitic being low porosity, excellent porosity in the siltstones, and then, you know, between clay rich to good TOC to TOC rich in the different mudstones. So we can start thinking of reservoir quality in that way. Moving on into the type of organic matter, we can look at the hydrocarbon generation potential. So plotting TOC and S2, and Lucy Coe has done a lot of this work, and Sunjun and Tongwei get involved in sort of the organic chemistry description. You know, I kind of team off of their observations and their result, and I have that advantage to be able to work with them. And so you can see, generally speaking, you're looking at sort of good to fair hydrocarbon generation potential for these. The pink chemofacies does sort of jump up a little bit higher, but you also get some of the pink chemofacies that drops down here. So it's a pretty big range of hydrocarbon generation potential. Thinking in terms of depositional systems, how this TOC got here, we can plot organic matter, TOC, total organic carbon content, versus molybdenum. And so we can start thinking of what was the basin doing, or what was the sort of basinal history during this. And overall, there's not a lot of evidence that there was really kind of Black Sea style restricted basins. And in contrast, during this pink chemofacies, when we're getting really elevated nickel and molybdenum, it's a open to weakly restricted basin. And so I just want to use this as an example of, we can really start, when we put all this information together, we can really go to lengths to try to better understand not only reservoir quality, but the geological history of these basins and the infilling history of these basins. Working with James Green at NewTek, we've been able to look at MICP data. So we're looking at median pore throat radius. This is how the median pore throat radius distribution. So you're not only looking at the porosity, but you're looking at the distribution of the pore throat radius. And that's one of it's not everything, but it's one of the things that's going to go into to understand the permeability of these chemofacies. And so we selected the samples based on their chemofacies, and then James provided the results from NewTek. And so this helps us better understand, again, in terms of reservoir quality, what's good and what's not so good. And as expected, those siltstones have the highest permeability. As a note, the size of these symbols are scaled with respect to their porosity. And so these here have the highest porosity and the highest, predicted highest permeability, certainly the highest pore throat radius. And that's in stark contrast to the dolomitic, which have the not only the lowest porosity, but the lowest permeability up on this at this East Vermejo core. The mudstones, though, are pretty variable, but still have, God, I keep hitting that, still have a relatively high porosity and sort of, medium to good permeability. So you can take all this information, and now you can start thinking in terms of what's going to be a good self-sourced mudrock reservoir, kind of typical of an unconventional system, versus what's going to be a good storage reservoir. So we can bundle all this data and really start to classify the chemofacies and describe them in terms of more than just their chemistry. Describe them in terms of their depositional environment, and also in terms of their reservoir quality. And I've sort of color-coded these dark gray. These are the self-sourced mudstone reservoirs. So these are the ones that have good porosity, have good organic matter content, are likely to be self-sourced, or could be self-sourced, and can also store, but they might have lower permeability. These here in the sort of lighter gray, these are the siltstones and the laminated siltstones. Good reservoir quality, relatively poor hydrocarbon generation potential, but good reservoirs. And so if oil is migrating around, good storage potential here. And then you get to these dolomitic ones, and these are basically the permeability barriers. These are the ones that they don't have a very high storage potential. They got low permeability and poor source rock potential. And I can't say much about calcareous mudstones, but I can always go back and add more data as I go. Okay, now let's take this and look at it in terms of a stratigraphic stacking framework. And so this is from the East Vermejo core. You can see the chord interval right here, and you can see my chemofacies stacking pattern right here. And I mapped the contact between Third Bone Spring sand and Wolfcamp X right here, just loosely tying it as a sequence boundary. And so you can start to characterize or look at a better characterization of the distribution of these chemofacies across. And so you can see some pretty stark contrast, and you can think of it in terms of a pie chart. In the Third Bone Spring sand, over 75% of Third Bone Spring sand here, the East Vermejo core, is dominated by these argillaceous siliceous siltstones and these quartz siltstones. So you're ranging from excellent storage, high permeability, to good storage potential, the variable source rock potential, and lower permeability, I should say. And then you have these other chemofacies that constitute 20% or so. They may not be important in terms of reservoir quality, but they may be important in terms of geological interpretation. And that's in contrast to the Wolfcamp XY below it, which has a much wider range of chemofacies. And again, like I said, you've got these siltstones that kind of map the base of Wolfcamp X that are overlain by these calcareous mudstones on top. And you can see the pink, that's where a lot of those nickel and molybdenum rich mudstones existed. So a lot of source rock potential here, a lot of potential for self-sourced mudstone reservoirs. All right, there's a trick question. Can anyone see what's wrong with this? Is there anything that stands out that should be a surprise? Anyone there that's unmuted that could see something that just doesn't seem right? Okay, I'll answer it. Here's the chord interval for the East Vermejo, but I've taken and I've mapped and I've predicted the chemofacies across the entire interval of all the way to the top of the Third Bone Spring sand and all the way down to the Wolfcamp Y. And I don't have any rock there. So how did I do that? Well, I did that by tying into my chemofacies model wireline log response. And so what you're looking at here are wireline log response for gamma ray, resistivity, neutron porosity, bulk density. And I was able to, it's hard to do, but when you line up the cores correctly, you got to do a different sampling rate. We'll talk about that offline. I was able to build in all the wireline log responses and then run another decision tree model that allows me to predict chemofacies across the entire interval. And so now I'm not just based on if I want to describe Third Bone Spring sand here, I'm not just stuck analyzing the chord interval. I can take it across the entire chord interval. So this is this is the beginning of that upscaling, taking the chord data to wells that don't have core. So how do we do that? Or how is the decision being made? Well, here's my chemofacies. It's actually based on 5 wireline logs. I added a photoelectric absorption factor, and these are histograms showing the wireline log response for each of the chemofacies. And so you can start to see some of the differences. So for example, the argillaceous silicious mudstone and the siltstone, those can be distinguished based on gamma ray alone, but you'd never be able to distinguish the this mudstone and that mudstone or the calcareous mudstone based on gamma ray. But if you throw in photoelectric factor, well, then you can distinguish this mudstone and that mudstone and start to distinguish that. And so it's the same kind of thought process as what's going on with distinguishing chemofacies based on chemistry, but we're doing it based on the wireline log response. So we're adding this into the decision tree model. We're running the model. You can look at the feature importance for each of the wireline log responses. You can see it's kind of equally distributed across all of them. So all of them are sort of playing a role. You can go into the confusion matrix and you can see where it's working and where it's not working. It doesn't work as well as with the chemofacies, but that's to be expected for a lot of reasons. One of them is that wireline logs average a much larger area. And so you expect you're going to get a lot of false negatives and false positives because one 6-inch chemofacies is going to be affected by the chemofacies that are stacked around it. And that wireline log response, if it's got a resolution of 2 feet, well, it's going to average a lot of things. And so we don't expect perfection for sure, but 70, 80% is pretty good. And that's about where we are right now with this chord interval. But we can always go back and see where it's failing, and we can use that to try to improve the model. So here's one method of model validation. This looks like what I presented in the previous slide, but what I'm adding here, these are the chemofacies. Boy, keeps going back. These are the chemofacies that are predicted based on X-ray fluorescence, and these are the chemofacies or electrofacies that are predicted based on wireline logs. And so you can see how the models are matching, and you can see the model's excellent. Fine, it loses a little bit of resolution. So for example, these thinner bedded pink intervals here, it expands out to one giant pink interval. At the scale that we're interested in to define reservoir quality, that's nothing. These dolomitic intervals, it's coming up a little bit bigger than you see here. Again, the overall theme and the deposition of the sequence or the stacking of the chemofacies, it's really no different between electrofacies predicted and chemofacies predicted. And so this is telling me that, well, it's 2 things. One of them, the model's working, but secondly, it's telling me that yes, this is a way forward to take core data and apply it to wireline log and upscale it across the basin. And this, in my opinion, this is one of the big goals that a lot of us have been working on for a long time. So I just have a few more slides to summarize it and kind of show you where we're going with it. This is just looking in terms of pie charts for the chemofacies abundance. And this is looking for Wolfcamp XY. And we're just I took this model and ran it across wireline logs for 5 chord intervals. And so I took a couple from up here, kind of up on top of the submarine fan, and then 3 down here that are distal down here. And you can see, as expected, the chemofacies abundance is changing. And so here, we get a lot more of these siltstones and well, mudstones, but the laminated mudstones up here, these are going to be good reservoirs. These are the quartz siltstone rich ones. And you see the same thing kind of at the Eastern Mayho, really good reservoir. But we move off that complex down into the basin, and everything changes, and it's just dominated by, at least over on this side over here, it's dominated by this the organic rich mudstones. So even within a single formation, along a transect, there's going to be a big shift in the abundance of chemofacies. That's going to result in a big shift in the style of deposit and the reservoir quality of it. And so what I hope we can start doing now is using this information to understand the reservoir quality across the basin. And we can also use this information to understand the geological history. And I can show that in terms of this one. I'm still a little bit confused by it. It's a lot more carbonate-rich mudstone over on this side of the basin, down by the Bush core and the Marsden core. More work needs to be done. Obviously, I'm at the edge of kind of my Isopack maps. I'd like to know what's going on down here to see if what's causing all that carbonate-rich mudstones to come in. We can do the same thing for the.
Toti, sorry to interrupt you. Could you finish like a wrap up in the next 1 minute? We have lots of questions, good questions too. Yeah.
Great. This is my last slide. Yeah, so I'll just skip over this. This is going to be a repeat of what you saw for the Wolfcamp XY, but it's for the third Bone Spring sand. Similar style, but the point is we can take all this core information and we can start populating core data into our wireline log models. And we can do that in terms of not only predicting chemofacies, but we can upscale to inform the wireline logs, but we can also start to make much higher resolution mineral models, organic matter models, porosity models for the core intervals, and really start to look at where these properties are. And I'll probably say this for questions, because my guess is that these are the questions: is how far can this be extended? And obvious concern. Well, successfully, I feel very successful at taking a chemofacies model and expanding it across a basin if we're working on XRF data. Once we step away too far from a chord interval, you got to be careful with the attributes. There's no way I'm going to take attribute data from Eastern Mayho and extend it down to the Southern Reeves County, but we can get that attribute data from other chord intervals. And wireline log, I'm assuming this is going to be a question, same issue, got to be careful with that. And so what it gets us to is this sort of thinking in terms of this decentralized and distributed network of training data sets that are organized by formation. And we can start pinning off different areas where we have chord intervals. And I just show you in red, this is where I have chord intervals. In black, these are where we have wireline logs that we can tie to. And so we can start tying this all together and get away from this centralized thought and start working in a sort of decentralized and distributed network and try to pull this together, and it all sort of lives and breathes together and kind of informs itself. I'll skip this. And the conclusions here, we've got 8 chemofacies. It captures the elemental variance. I can describe these chemofacies in terms of the rock attributes. I think we can show quite well how the reservoir quality changes from north to south. And I think I can show quite well that this decision tree is a promising model in terms of using to machine learn a lot of the data that we collect. And I'll just point out, none of this is possible without the support that you get from people around you. And that goes to the core warehouse with Rudy and Brandon and Nate, who are excellent in the core warehouse, Joseph for helping me out, in Petra. Respect the people who generate the data. Evan, Harry, Scott Schultz, Michael Newman, so people who are involved in generating data, they get their hats off to them, because it's not easy to generate these data sets. And also, obviously, to the MSRL sponsors who helped fund this project and provide questions that directed the research. So thank you, and I'll take questions.
Thank you, Toti. This is a great talk, lots of good materials and very informative. So we have lots of questions actually. So for the sake of time, I'll just read through them. Okay. So the first couple questions is from Louis Mathilde. So she has a couple questions here. The first one is the data shown on this cross plots from one well or multiple wells. How do you QC the XRF data before using it in the workflow?
Yeah, great question. So there's a whole scheme that I go through with outlier detection. And so, first off, all the XRF data is calibrated off the Mudrock calibration. And so it's already semi-quantitative calibrated. There's a lot of work that's done on Evan's side with, if sulfur is elevated, get it out of there. Sulfur will screw up your results to no end. Once I get the data and it's been QC'd by Evan, then I go through another series of QC for outlier detection. And I generally take any of the outliers and I define outliers as anything that has about 4 standard deviations away from the median for a data set. I take those out, and that's when I start doing my unsupervised classification. And so that's the most of my QC on XRF is done using that.
When you say outlier detection, do you mean by depth-wise or by element?
By element. So, and that's important. An analytical outlier, by my definition, is just might be important. For example, if someone XRFs pyrite, you're going to have huge iron and sulfur spike. If I put that concentration into, certainly if I normalize that data, put that into a normalized data set and run like principal component analysis off of it, it's going to screw up everything because it's going to drive the variance. So it's an analytical outlier. That said, I always go back and I put my analytical outliers onto the maps that I'm looking at, and then I can sort of define, like, is that geologically important or not?
Thanks.
Yeah.
And our next question is from Sibrits. So the question is, do you do any type of preconditioning or filtering on data before running the MVAR models? And next question is, which decision tree software package do you use?
Yeah, so for that one, I didn't put, all this is available on my GitHub account. I can provide, email me and I'll give you the link to it. I'm using XGBoost Decision Tree out of Python, and I can provide all those on my GitHub.
That's really cool. And we have another question from Luis. Yeah. So how were actual chemofacies obtained?
So supervised classification. I start this game using unsupervised, and I think everybody should. So principal component analysis still plays an important role, and use unsupervised techniques when you're exploring. And if you're not exploring, you might be missing out on something important. So I always start with unsupervised, and then I go back to those core photographs and I look to see, okay, what is this actually picking and where's the overlap? And so that's when I get into the supervised classification. And so the training data set that I built is supervised. And my sort of rules of supervision is, what fabric is it picking it up? I'll relook at it through the X-ray diffraction to kind of, I'm trying to bend down to the smallest variance for any one chemofacies. And what's cool about this is that as you make changes to your training data set, and again, this comes out in CorePy, it reruns the model for all the information that all the core data that I've got. And so I can real time kind of check the effect that decisions or that change is having across the board.
Cool. Hope that answers Luke's question. And the next one we have is still from Cibrix. So could be interesting to digitize the RGB colors of the core photos to correlate against faces. Yeah,
no, absolutely. There's one of the member companies in the MSRL consortium. We're working on that together. Yes, it's going to work and it's not going to work. It depends on the core. Those have to be really good core photographs to make that work. And then when you get down deep into the basin, these Mudrock systems, they are kind of all black, unlaminated, dark, nondescript rocks for the most part, not entirely. And so, I think the answer is going to be, sometimes that's going to be great, and sometimes it's not, but I'm definitely interested in doing that. As well as, doing this from a straight, kind of, you take some of the the pioneers in this core characterization. Take Bob Laux and the way he describes fabric and his lithofacies across it. We can get a lot of information based on those descriptions that someone like Bob does to put that into this decision tree. And that's one of the reasons why I don't think Bob knows this yet, but one of the reasons I'm excited about moving towards decision tree is we can start bringing in the types of descriptions that he does. I think that's going to get really powerful.
Cool. And okay, we still have several other questions. The one of them is from like Hong Liu Zhen, and he just asked for your comments on multiple thin carbonate-rich baths improve brittleness, oil saturation, and frac results. You have any comments on that, Toti?
Yeah, no, absolutely. It's those carbonate-rich. Well, I guess Hong Lu, are you asking? Is it if you just have a single kind of meter scale carbonate interval versus kind of multiple thin beds across that meter scale, and how will those behave differently? Well, I guess I just answer the question as I see it. Absolutely, the brittleness will increase with that carbonate. The oil saturation, that's some of the work that Tong Wei and I are doing right now. Tong Wei's done a lot more of that before me, looking at oil saturation in the carbonate layers. And that's between, and I see one of the questions here of self-sourcing and biomarkers. There's a talk that Soon Jun is going to give at AEPG that's using biomarkers to look at evidence of oil migration versus self-sourcing. And we've got ongoing conversations on that. And we're starting to hone in on those mudstones in that Wolfcamp X interval to see if there really is evidence of self-sourcing there or not. So that'll be that takes a second another talk to answer that one.
Cool. And we have another question. I think we still have some time to get 2 questions. The one is from Chi Wang, and he asked, could some sort of resampling of the wireline data help?
Yeah. So what I'm doing there is, wireline data, resolution 2 feet more or less, but it's collected at 6-inch intervals. XRF data is collected at a 2-inch interval. So the only thing I've done to the wireline log is I've increased the sample spacing, but I haven't done anything to change the wireline log response in any way. And so all I've done is I've upsampled the curve that exists, and so I can match it directly with my XRF data. I've had conversations with Jit over here at BG and Carlos Torres over at PGE, and we haven't gotten too far on it yet, but that's the next direction to take this to, is really work with some real petrophysics and try to do a better job of informing those. And I can only imagine, I'm not a petrophysicist, so I can only imagine the effort that could go into that, and I'd love for that level of collaboration to happen.
Totally. Someone asked if you can provide the details on the talk. You just recommend for detailed information.
Yeah, we got one paper that just got accepted to AEPG, so it's not going to be out for a while, but it just got accepted this week. It's these sort of tools on the applied to the Austin chalk. This I'm writing up. Give me a shout, call me. We can talk, and I do have some of this available on my GitHub account.
And one last question we can answer for the seminar is the Jerry Jensen. He asked, have you identified what factors are present in the chemofacies that each log is responding to? Yeah,
well, okay, not exhaustively, but looking at the like in the photoelectric factor, on that wireline log, that's clearly picking up the mineralogy. And so you can see a real strong distinction between the carbonate rich and the quartz rich. And I see that one very closely. Same thing goes with gamma ray, although the resolution doesn't seem to be as good, or distinction of the resolution between the silicious argillaceous, the mudstones, I should just say, because the mudstones do have a lot of clay. So gamma ray is picking it up. photoelectric effect is picking it up. Bulk density, you can see the distinction there between the carbonates and the the more quartz rich. Resistivity is obviously the one that I'm concerned with, and resistivity is the one you got to be careful with. And that's why, as much as I say we can integrate and we can take things across the basin, it's with an asterisk. It's be careful. And resistivity is going to be that big one. That resistivity log is going to change on fluid saturations, on salinity, on a variety of factors. And so I'm very cautious on how far I'll take. Well, let me put it this way. I do not envision one wireline log chemofacies model for the Delaware Basin for any one formation. There's going to be multiple. You're going to build it out kind of in specific locations. But I do envision a single chemofacies model for a formation run off XRF across the basin. As long as we've captured all the facies, and I think we have, then I think we'll be fine there. Consider that Wolfcamp XY is about the hardest one to do in these mudrock systems. Wolfcamp A doesn't vary as much as Wolfcamp X does across the basin.
Cool. It's already like 10:03. I think some people may sign up, but thank you for joining the seminar. But if you are still interested, we can continue to cover the rest. I see like 3 questions.
Yeah, sure. I'll stick around.
Yeah. So those are very good questions. And there's one from Tim Huang. He asked, have you got a chance to compare your predicted what is the resolution quality with a production performance in wells with no data? No, I've not compared this to production data yet. Yeah. And obviously that's the, from the geologist side, I mean, this is sort of built up from a geologist perspective. And so, it's taking the geology, using the chemistry to help, bin things into clusters. But then the next step there, of course, is to understand how does the geology affect production? And I think this is going to give us a much higher resolution way of answering that question. Yeah, I think so too. And another question is from David Carr. He asked, have you thought about how thin that chemofacies, like a 2-inch resolution, could be upscaled to meet log resolution, which is like 2 to 3 feet? Like, for example, create megafacies from chemofacies might provide a better match to log data. Yeah, I guess there's 2 ways to look at that. One is, well, let's just start and see if we can use the chemofacies to upscale log data and better inform, even though log data is capturing a 2 foot, let's just stick with that, a 2 foot resolution. There's a lot of information there that is, and a lot of variation within that 2 foot that we might be able to better inform the sort of swings of those curves with a higher resolution. And so, I would, and maybe this is being too optimistic, but I would like to start the conversation of, can we actually try to resolve out things below log resolution using this or not? And if we can't, then fine, we can start averaging chemofacies. But I get nervous when you start averaging because we're not taking advantage of what we got. So I want to be careful with that, but definitely open to understanding what the limitations are on the wireline side. Thank you, Toti. The last question I see in the chat box is from Simon Hughes, and he asked, you mentioned that you were looking into using drilled cuttings-based data. Can you expand? Yeah, so we're already doing that. I haven't reported it yet. It's a different problem, or it's a different question that you're going to ask with drill cuttings. The issue with drill cuttings is that it's averaging a much larger chord interval, and quite frankly, it's a mess. You don't have good integrity of sample like you do with core data. So you're never going to be able to take drill cuttings data and kind of build out really high resolution information. The way I see it working with drill cuttings is that we are going to, we'll powder the drill cuttings, we're going to XRF them, and then it becomes a mixing model problem. Which chemofacies are in that drill cutting? And what's the relative abundance?
And so it's a really complicated mixing model, because you've got, in this case, I've got 8 possible chemofacies, 1 drill cutting analysis, say 26 elements to kind of work with. And, I would love to be able to say, we could tell you exactly the abundance of each chemofacies within that drill cutting. I expect what we're going to get to is, well, let's just ask the question. Let's look for one specific chemofacies, and can you tell me whether or not that chemofacies is present in that drill cutting? That might be an easier question to answer. And then if we get success with that, then we can start seeing, okay, well, maybe, can you tell me 2? Can you tell me with and what level of certainty do you have that that 2 of these chemofacies exist in that drill cutting? That's the direction I'm taking that. And so we have in Delaware Basin, we've got, with one of our MSRL sponsored companies, we've got a really good data set where it's a chord interval and drill cuttings collected from nearby. And so we're beginning that to look at that right now.
Cool. Thank you for asking those questions, and thank you, Toti, for answering them. Those are very good discussions. So I do not see any other questions in the chat box. So yeah, if there are no more further questions, I think this will be the end of today's seminar. Thank you again, Toti, for the great talk. Very good materials and very informative. And also thank you everyone who joined us today, and hope to see you in our next Friday seminar.
Next week will be Dr. Ben Smith of Caltech talking about geochemistry and sedimentology of Earth's history.
Awesome.
Awesome.
Thanks,
Thank
Toti.
Thanks, Kelly, and thanks, Jan, for organizing all this. Appreciate that.
Sure.
Thank you, Toti. Appreciate it. You have a great day.
Yeah, y'all too.